Welcome to my video tutorial program code Chapter 6 Social Security 1.g from my book on public economics. Now in this tutorial we compute the quantitative effect of an abolishment of pensions. So we will see that it significantly increases savings and the capital stock, and the effect on welfare will be tremendous. Now these are not just a couple of tiny percentage points, but we will see that, for example, if we go from the situation of no pensions to one with a replacement ratio of pensions of 33%, the savings drop by more than 60% and welfare decreases by more than 35%. So what this means is there are huge welfare gains, huge economic gains from abolishing pensions, but of course there's also a detriment to it. We need to sacrifice it during the transition. So we will also look at the dynamics in this problem. So if we abolish pensions, this also means that there's an initial drop in welfare for the transition generation. Now, let me issue a warning here. We neglect many aspects in the model which you find in the real life. So we do not have lifetime uncertainty. So of course a public pay-as-you-go pension system provides insurance against the risk of living a long life and healthy life, because then you need lots of savings. And other aspects that we neglect, for example, income uncertainty. Now, this will be the point of discussion in the remaining parts of my book in chapter 6.4. But nevertheless, the point remains that even if you take a more accurate demographic structure of the economy, for example, in a 60 or 80 period overlapping generations models, you still find that the abolishment of pension has significant effects on aggregate savings. So in my book, I find that abolishing of the US social security system would result in an increase in the capital stock by approximately 1/3. And welfare effects are also significant. Now, my video lecture is structured as follows. First, we look into the economics, and I will present to you the two-period overlapping generation models in which we derive these results. In the second part, we will study the program, the Gauss computer program that computes this model. And then at this point, you might want to halt the program and try to compute the exercise that we look at in this third part yourself first. So what we do is we look at the case, do some sensitivity analysis to our results. We look at a different intertemporal elasticity of substitution. Rather than at 1, we look at an intertemporal elasticity of substitution equal to 0.5 and wonder if our results remain, whether our results are robust. You should always look into these issues in overlapping generations model, because we do not really know this parameter sigma, the inverse of the intertemporal elasticity of substitution, the so-called relative risk aversion coefficient. And we find that in this case our results are even more pronounced, even stronger than the one with an intertemporal elasticity equal to 1, where we have log utility in consumption. Now let's first go to our economic problem, and therefore I would like you to switch to our slides. So please download the slides from chapter 6 from my homepage, chapter 6 on pensions, and go to slide 24, where our computational problem is described. So we study the pay-as-you-go pension system in a two-period overlapping generations model with inelastic labor. Our period length is approximately 30 years. So that agents live 60 years, 30 years as a worker, 30 years as a retired. The lifetime utility is presented by equation 16. So it's additively separable in utility from consumption today, which is log utility, plus discounted utility from consumption tomorrow, minus disutility from labor at young age in period t. Now we can ignore the third additive term, the disutility from labor, because we consider exogenous and constant labor supply equal to 0.3. Now our pay-as-you-go pensions takes the contributions dt from the young generation in period t and transfers these as pensions to the old generation. So the social security budget constraint is provided by the bottom equation on slide 24. The young agents, which have a number nt, provide contribution dt, and this is equal to total pensions, so the number of old agents, which is equal to nt minus 1, the number of young people in period t minus 1, times the pension in this period t. So if you divide by nt minus 1, you have that the pensions are equal to 1 plus n times contributions dt. N is the population growth rate. When we look at a system of constant contributions d over the time, we know that pensions are equal to 1 plus n times d, and this results in the intertemporal budget constraint 17. On the left-hand side, you find wage income plus pension income, discounted pension income, minus social security contribution. So our net present value of income is equal to the right-hand side, the present value of consumption, which is consumption today plus discounted consumption in old age. From the first order conditions 18, we can derive the Euler equation according to which consumption in old age, C2, is proportional to consumption in young age, C1, where the proportionality factor is given by beta times 1 plus r. If we substitute the Euler equation into the intertemporal budget constraint, we get an expression for C1, which we can again substitute into the equations for savings. And our equation for savings gives us a description of the capital market equilibrium that is presented by equation 19. So for the case of constant contributions D, we have derived the capital dynamics of the capital stock. In equation 19, you still have the factor prices WT, the wage rate, and the interest rate RT plus 1, which is given from the profit maximization behavior of the firms. So for a production function, a Cobb-Douglas technology described in equation 20, our wages and interest rates are given by the marginal product of the capital stock and the labor supply. So this is provided by equation 21a and 21b, which we can substitute into equation 19 to get the dynamics for the case that contributions are constant. If contributions are non-constant, the case we will consider in the transition, then our dynamics are described by equation 23. So in case the contribution at young age dt in period t is different from those provided by the young cohort in the next period, dt plus 1, we need to distinguish this case, equation 23, from equation 19. So for example, we will consider the case that in the period 0, t equal to 0 and equal to 1, the contribution rate is 30%, and in period 1 it is announced, okay, from now on there will be no further pensions, so that the cohort that is born in period t equal to 1 has to pay the pensions of the old generation, but itself will not receive a pension when they are old in period t equal to 2. And we will compute this and therefore need to distinguish dt from dt plus 1. The model is parameterized as follows. We use a production elasticity of capital equal to 0.36, a discount factor beta equal to 0.40. So this amounts approximately to an annual discount rate of 3% if we consider a period length of 30 years. and a population growth rate of 10%. So this amounts to a population growth rate, an annual one, equal to 0.3%. So this is really close to the American economy. And we consider two steady states in the first part of our computation, one where without pay-as-you-go pensions, so pensions are equal to zero, D equal to zero, and one where the contribution rate is 30%, so 30% times the wage times the labor supply, and therefore the pension replacement ratio is equal to 33%. The pension replacement ratio is described by pensions relative to wage income, and since pensions are 1 plus n times d, we have 1.1 times 30%, meaning 33% of our gross wage. So in the United States, of course, the pension replacement ratio is closer to 50%, while the contribution rate is equal to about equal to something like 8-9%. This means that our case that we study here is somehow in the middle of the system that we observe for the United States. Now let me get to the results. The case, the steady state without public pension, is characterized by a capital stock equal to 0.0182, labor supply equal to 0.3, and output equal to 0.109. This is our benchmark case, so the welfare change, of course, compared to this benchmark case must be 0. If we increase the pension replacement ratio from 0 to 30%, so introduce a pay-as-you-go pension system, the capital stock decreases to 0.00687. So the decrease amounts to 62%. Since labor is constant and the two production factors are capital and labor, output decreases to a smaller extent than capital stock, but still by 29%, from 0.109 to 0.077. Now notice the huge welfare effect. The welfare decreases in the case of public pensions by 38%. So to interpret this number, we measure it by a consumption equivalent change. This means if we look at the situation with a pay-as-you-go system to make the first steady state without public pension comparable to it, we had to diminish consumption in each period at young age and at old age by 38%. Only then would these two scenarios be comparable. So without pensions, a reduction of consumption of 38% makes the situation equivalent to the one with public pay-as-you-go pension. Now this is huge number, tremendous. So we hardly find any such big numbers in other computational dynamic general equilibrium analyses. So for example, in the case of the welfare cost of inflation, economists have tried to measure this in new Keynesian models and in standard, for example, by eliminating the fluctuation, the volatility of inflation. And what they find as welfare costs are something like 0.1, 0.2 or 0.4% of consumption equivalent change, but nothing remotely close to welfare changes of 38%. So this is a huge number, and for economists this means a lot, and of course we need to act in the case of these numbers if we should reform our public pension system. Now one question, of course, is this result robust? So we might wonder, well, the demographic structure, we have basically almost the same size of young and old people, so they are at the relative size is 1 to 1.1. So this doesn't seem accurate. Now if we introduce a more realistic demographic structure, perhaps look at an overlapping generations model with more than two cohorts, let's say 80 cohorts, and make it more realistic, introduce a survival probability so that we have the demographic structure of the United States. And we do this in later chapter 6.4. So let's go to slide 80 in this chapter and find the results for our large-scale OLG model. And look at the second entry column, which is the case without pay-as-you-go pensions, hypothetically in the year 2005, so that the replacement ratio of pension is 0. In this case, our capital stock amounts to 1.551, and our of course, our contribution rate is equal to 0. Now, if we compare it to the case with a pension replacement rate of 50%, which we assume to be the present case, the empirical case, we observe that the capital stock declines to 1.110, sorry, and that the contribution rate rises to 8.53. So this again implies a decrease in the capital stock by 28%, almost 1/3. So this is of course significantly lower than in the simple two-period overlapping generation model, but it shows us that the effect is everything else but negligible. Now let us go to the computational exercise. For these reasons, I would like to switch into the Gauss code. And let's take a look at chapter 6, Social Security 1.g. I would like you to load this one into your Gauss editor, adjust the working directory in the top menu bar so that the toolbox.src, our source file which contains the nonlinear equation solver, is in the same directory. So make sure all our computer code for chapter 6 is in the same directory and that the working directory is the same. Now I would like you to adjust the plot style 0 or 1 depending on your Gauss version. So in line 21, if you have Gauss 19 like me right now, use plot style 1. If you have a very old Gauss version like 13, 12 or older, use plot style equal to 0, save it, Control S, and run the program. First thing you need to make sure is, does the program work? And it should give you a result like the one displayed on the right hand side of the screen. And in the first part we compute the steady state capital stock for the case of no pensions. It amounts to 0.0151 as given in the lower right hand side bottom. And in the next part we compute the capital stock in the case of a pension of 30%. Sorry, there's a small mistake. Let me see if I have the right computer program. Sorry. So sorry, this was wrong computer program I started. Sorry for this. Steady state capital stock is 0.0181 without pensions, and with pensions it's 0.006865. The dynamics of the capital stock, if we move from a system with Social Security, like the one in the United States right now, to one without Social Security, the capital stock increases over time. The dynamics are displayed in the figure, and we also have effects on welfare. So in the case of pensions, utility is 38% below the new steady state utility, and during the transition utility even decrease in the first period, in the first generation where we introduce the change in the pension system, so that we say to the first generation in period T1 t equal to 1 to the young generation. You will not get a pension in old age, but you still have to pay for the present old generation. Their utility drops. You can see a significant drop, and only the generations born after period t equal to 1 are better off. Now let's get into the computer code chapter 6 social security 1.g. And we describe the parts before we go into the details. So in the first part we have the common between two @signs. All the text between these two @signs are ignored. We have the computer name, we have the description of what it does, and we have the author and the date when it was programmed. Now in the first part we just clear the memory and load toolbox src into our working directory into our memory so that we can access the nonlinear equation solver that is stored in toolbox.src. In the first part we have the parameters. So we set the exogenous labor supply equal to 30%, alpha equal to 0.36, beta equal to 0.40. Notice that we cannot use the variable name beta because it is reserved in Gauss, so we have to use beta 0. Same holds for variable name sigma later on. And we have a population growth rate equal to 10%. The disutility parameter nu 0 and nu 1 are copied from chapter 6 social security 2.g and are of no interest right now. We can ignore them. In the first part we compute the steady state for no pension system, so the contribution rate is set equal to 0. In the second part we compute the case in line 87 where the social security contribution rate is set to 30%, and in the fourth part we compute the transition. Now let me also show you the procedure that we use. The procedure case steady computes the nonlinear equation that is describing the steady state. So if the capital stock is constant in period t, k0, and also in period t plus 1, our nonlinear equation that describes the steady state is provided by equation in line 197. So please compare this to equation 19 in the slides. They are identical. The procedure K-dun describes the nonlinear equation in 23, where the contribution of the young and the pension in old age, so the contribution of the young in the next period, may be different. So this is important for the study of the dynamics. So this is equal to equation 23. So for exogenous given capital stock K0, we provide the argument K1, next period capital stock, to this procedure, and it gives us the solution for equation 23. If it's fulfilled, our variable y is equal to 0, otherwise it's not. And we're looking, of course, for the solution of this equation, which is the root K1. And in the procedures wage and rate, just compute the marginal product of capital and labor, which are equal to the factor prices respectively. And we also have a procedure that simply sets the graphics. Now let's go to line 46. So let's debug our program. So press the sign for debug and go to line 46. So just jump over our parameterization of the model and just go to the computation of the steady state for the case without a pay-as-you-go pension system in line 46. Therefore, move your cursor to the top menu bar and press the arrow that runs to the cursor to line 46. So we now move around in the debugger using the arrow signs on top of the menu bar, and with the key F9, step over, we move from line to line. So what we do in lines 46 through lines 49, we set up a grid of the capital stock K, 1000 grid points, equispaced grid points from 0.001 up to 5 in order to find a good initial value for our nonlinear equation solver of the steady state equation. We store the values of K steady for all these grid points in the variable yk. So for example here, when we go to the first iteration here, I equal to 1, we use the value k 0 equal to 0.001, the first entry into our vector k, our grid over the capital stock. And now we step into this procedure k steady, compute the contribution d. Our contribution is equal to 0 because we set tau equal to 0, the social security contribution. And for our capital grid point 0.001, we compute the nonlinear equation 19, our steady state equation, and see if it's equal to 0. Well, it's close, but not completely close. It's minus 0.0059. And we return to the calling function. And we continue this in this fashion and compute all the points on this grid. So let us jump out of this iteration, out of this loop into line 59. So we have now computed the nonlinear equation that characterizes the steady state on different grid points. And of course we look for the solution for the root that's closest to 0. So if we study the solution here, the vector yk, we see that this is the case for the grid value 4, for the fourth grid point. So let's see, this grid point k is equal to 0.016 is our starting value. So how do we implement this in Gauss? Well, we look at the minimum of the absolute value of yk. Then we get to this. So the minimum of the absolute value of yk is the fourth entry, 0.001. And this is computed by the command in line 59. So if you do not know a command like minint c, which stands for the minimum indicator of a column vector, of the column, just use the help function, which you can call during your debugging, and search for, let's say, minIndex c. And it provides you with the purpose of this command, returns a column vector containing the index of the smallest element in each column of a matrix. Since our matrix is a column, this just returns one element, which is 4, the indicator of the entry in the capital grid K. So let's go back to the debug mode. And here we find our K init is 0.0160 as expected, and this is the fourth entry in our capital grid K. Now in line 69 we solve the nonlinear equations problems by invoking the procedure fixVal vmn1, and we have to provide the initial value k init, and we have to provide the nonlinear equation, which is k steady, the procedure. And notice that we have to insert the ampersand in front of k steady so that Gauss knows this is a procedure, this argument is a procedure. And it computes the solution KSS, which is the steady state capital stock with no pensions, and provides the criterion vector crit. So if the first entry is 0, we know it's normal convergence, everything is fine. The second entry is the accuracy, so it's close to 0. And the fifth entry is the number of iterations, so it only took 2 iterations to get to this solution because we came up with such a close initial value here. So let us confirm this. So the value of our nonlinear equation for our solution is 2.1 to the power 10 to the power minus 8, and we can compute, with the help of this steady state value, we can compute the consumption, the steady state consumption at young age and at old age, C1SS, C2SS, as provided in lines 78 and 79, and the utility, which is log utility of consumption today and tomorrow discounted by factor beta, and our disutility from labor. Okay, now in line 87 we look at the case where the social security contribution rate is 30% and the rest is unchanged. So we can go through all these equations again and just jump into line 105 where we compute the solution to the nonlinear equation system now for social security contribution rate of 30%. Oh, sorry. And find out that this value is indeed KSSD equals 0.006865. Next, we show that we have the accurate solution by computing the value of the nonlinear equation K steady at this point, which is something 10 to the power minus 9. And again, we compute consumption in young and old age and utility. And in line 118, we compute the consumption equivalent change as by the formula provided in the book and in the slides. So we have a consumption equivalent change of 38%. The lifetime utility is much, much lower in the case of a pay-as-you-go pension system. Now we get in line 125, we get to the computation of the transition. We specified 20 transition periods. As we already saw, these are more than enough, so we have convergence within 20 periods. We store our capital stocks over the periods in the vector kt, our utility in the vector utility, and we initialize our first capital stock with the steady state in the case of a pay-as-you-go pension system. So we start from a state where the government provides public pensions and with the social security contribution rates of 30% and pensions are equal to 33% of wage income. So replacement ratio amounting to 33%. And we also have the initial value for the utility, and we compare the consumption equivalent change that would result if we compare it to the steady state without pensions. Now I is the index of the periods from 1 to 20 that we would like to study, and tau 0 and tau 1 are the social security contributions rates. Tau 0 when we are young in period t, and tau 1 when we are old in period t plus 1. So in the first period, I equal to 1, we just assume that the initial capital stock is a steady state capital stock, that the social security contribution rates in the next period are 30%, and we solve equation k dun, which provides us with the next period capital stock K1. So for this reason, go into procedure K dun, place the cursor in line 207 and press run to cursor. So in this case now, D0, our contribution in young age is 30% of the wage, which amounts to 0.04786. And for our starting value K1, which we just took to be the K0, 0.0068, the contribution next period by the young generation is 0.014. And for this we can compute the nonlinear equation as the dynamics of the capital stock as a function of K1. Notice that K0 is given, so K0, the capital stock is a state variable. We need to find a solution for the next period capital stock K1 with the help of equation 31, and therefore we have to compute also contributions today, contributions next period, which is equal to 1 plus n. 1 plus n times this contribution is equal to our pension, and this gives us equation 23. So we can step out of this and step out of the nonlinear equation solver to get back to line 145. So for the period in period I equal to 1, we have, we have computed next period capital stock K2 as 0.0068. So it stays constant because now we assume that for I equal to 2, which corresponds to our period t equal to 1, we announce to the young cohort, well, next period you do not receive a pensions, but you still have to pay for the old period, for the old generation, for the pensions of the old generations. So this is implemented here in this equation. Let's run to the cursor again. So if I is equal to 2, meaning period t equal to 1, the young do not receive a pension next period in t equals to 2. So tau 1 is equal to 0, but they still have to pay for the old generation, so their social security contribution rate remains at 30%. Tau 0 remains at 30%. Only in the next period the young generation does not have to provide social security contribution. And this will of course lead to a different value of K1. K1 increases to 0.00896, so this is the capital stock in period T equal to 2. Savings increase because young agents know they will not get a pension, so they have to save if they want to consume next period. So they increase their savings. And in the following lines, we save consumption young age, consumption old age, and we save utility and consumption equivalent change. And we can continue this computation over the next couple of periods when the contribution rates are always equal to 0. Now post the cursor on top of line 158, run to the cursor. We have now computed the whole transition of the capital stock, which is stored in the variable KT. We have computed the consumption equivalent changed. As you can see, compared to the steady state without pensions, in the old steady state it's 38%. In the transition it is minus 45%, and then it increases. So let's plot our results. First, for the case of the capital stock in period 1, when the change in the social security system is announced so that the young generation will not get a pension, they have to increase savings so that they have enough to consume from next period. And notice that the increase in savings is even higher for the following generation. The reason is that their income increases. They don't have to pay social security contributions at young age, so they have higher income, so they can save a higher amount, and the convergence to the new steady state accelerates. And after 4 or 5 periods, we are basically in steady state. And let's go back to the debug mode. And see the effects on the consumption equivalent change. As I already pointed out, the drop in utility for generation that is born in period 1, which has to pay contributions but do not receive a pension in old age, they receive a significant drop in welfare, which amounts to 7 or 8% of total consumption. And only the generations born afterwards, after period 1, so in period 2, 3, and so on, will benefit from a policy that abolishes pensions. So now go back to the debug. We have finished our debugging and stop the program this debugging by pressing the red square. So this terminates our computation of the Social Security 1.g of our effects of the pension system, pay-as-you-go pension system on savings and the transition dynamics. Now let's get back into our slides. Now we go to page 102. We look at the robustness of our results. You should always do this because we're not really sure about this parameter sigma. It may be 1, it may be 2, it may be 4. So empirical evidence is mixed. We are not 100% sure where this parameter lies. So let's do a sensitivity analysis for sigma equal to 2, which means we have look at as intertemporal elasticity of substitution equal to 1.5, so 1 over sigma. And then our utility changes to equation 56. Now, if you would like to figure out yourself how it affects our result, you may pause here, compute the dynamics, the different dynamics for this utility function 56, and try to change the program chapter 6 social security 1.g accordingly. If you would like to go on, then let's look at what happens together. Now for this utility function, we can compute the first order conditions 57 and the Euler equation 58. Again, we can substitute Euler equation 58 in the intertemporal budget constraint, derive pensions, and for the capital market equilibrium, we derive an equation that now looks a little bit more complicated because for sigma unequal 1, the terms, some terms do not drop out. Now we assume that pensions are given by 1 plus n times dt, and we have a social security contribution rate tau t. We can express our dynamics as presented in equation 106. We also have to adjust the computation and the computation of the consumption equivalent change. This is now different, so we have to use the formula presented on slide 108. Now let me show you the results first before we look how we compute them. The decline in the capital stock is even more pronounced. It amounts to 78%. So higher value of the coefficient of relative risk aversion sigma, meaning a lower lower intertemporal elasticity of substitution of 1/2, even increases the decline in the capital stock. And welfare effects are even more pronounced, almost 50%, so 49% if pensions are abolished, then our utility goes up significantly. Now we want to study this in the Gauss program. Therefore, let's go back to the Gauss screen here. First, what you should do is you should save your program chapter 6 social security 1.g under a different name. So if you implement changes in a Gauss program that works, do it under a different name so that you do not lose your old results. So I have chosen the name chapter 6 social security 1 IES05 for intertemporal elasticity of substitution 0.5.g, and I've adjusted the description of this case of this Gauss computer program. So I've inserted that it's now computes the case for sigma equal to 2 and then the date when it was computed. Now I will present to you the changes that are necessary in our computer program. You can also load this program from my homepage. It's provided with the other computer codes in chapter 6. Now first, of course, we have to specify that sigma, the value of sigma. Since sigma is a reserved variable name, I use sigma 0 equal to 2.0 in line 33. Now let's first go to the procedures that we need to adjust. We need to adjust the dynamics of the capital stock and the steady state equation. Steady state equation is changed to equation 217. So these two lines are adjusted. Just go through them and compare them to the equation provided on the slides 107 with our dynamic equation. So here we have set K1 and K0 or KT plus 1 and KT equal to the value of the capital stock that is given by the user when he calls the procedure case study. So K0 in this procedure is the variable KT and KT plus 1. Now let's go to the dynamic equation. Here we provide the value of KT plus 1 as the variable K1, and K0 is given. K0, for example, determines the wage in period T, while K1 determines the interest rate in period T plus 1. So in lines 237, 238, we provide the new dynamics. The wage and the interest rate equation do not change, and we also use a new procedure here, lifetime utility util. I have introduced this new procedure. You provide consumption in young age C1, consumption in old age C2, and labor supply L1, and U returns the lifetime utility as provided by the lifetime utility on slide 102. So these constitutes our changes in the procedure part. Now let's go on here in our main part of the program. We do not have to adjust anything up to line 78. So we have to change the computation of the consumption young age and old age in the steady state, which is now different, and the utility in steady state. The same holds for the case where we contribute the steady state for social security contribution rate of tau equal to 30%. So we have to change again line 118 through 120 where we compute consumption young age, old age, and the utility in the case we have a pension system. So this is abbreviated by C1SSD. So consumption 1 in young age in the steady state with the pension or social security contribution D. And we have to change lines 123 through 126 because now the computation of our consumption equivalent change CEC is different from the case with log utility in consumption. Next, when we compute the transition, we have to change the initialization of the consumption equivalent change in steady state. This refers to lines 140 through 143, and we have to change line 115 changes line 159 through line 168 are changed as well, again because the computation of consumption young age and old age, utility, and the consumption equivalent have changed. And that constitutes all our changes. So let's run the program to see if we get nice, neat results. So our steady state capital stock without pension is 0.0151 with utility of minus 68.76. Now if we have a pension system with a replacement rate of 33% amounting to a contribution rate of 30%, we have a capital stock of 0.003, which constitutes a drop in the capital stock of 78% and a drop in welfare as measured by the consumption equivalent change of 49%. And our dynamics of the capital stock look pretty much the same, at least qualitatively, and also our welfare changes. So our result seems to be robust with regard to the intertemporal elasticity of substitution, even more pronounced in the case of a higher value of sigma, and we have confirmed our analysis of our two-period model. So this terminates the exercise with regard to our, our sensitivity analysis. So I hope you have enjoyed the computation. If you have any problems, if you encountered any bugs, if the computer code does not work, please do not hesitate to contact me, send me an email, and it might take a day or two or a week or two before I answer, but I would be happy to reply to your emails. Thank you very much.